Good morning. As a part of our compiler's first assignment, we are going to explore GNAT compiler, which provides support for ADA programming language. ADA stands for GNU NYU ADA Translator. It uses GCC in the backend. The development of this project started in 1992 when USAF asked NYU team to build one free compiler for ADA to help with their ADA 9x standardization process. The first official validation of GNAT is done in 1995. It was developed by two universities, NYU team and Florida State University team, which was led by Robert B.K. Devar and Edmund Schoenberg in NYU team. Theodore P. Baker in Florida State team was responsible for the first design of concurrency concepts. GNAT compiler was sponsored by US government from 1991 to 1994. GNAT is transformed to GNAT Pro. In August 1994, the members of NYU team created the company Adacore Technologies, which provides technical support to industrial users of GNAT and has transformed GNAT into an industrial full-strength featured compiler GNAT Pro. That's how it became GNAT Pro, and GNAT Pro and GNAT are the words which are used in interleaved fashion. GNAT compiler is created for ADA programming language and it is open source. This compiler is written in ADA language. Initially, the team has written the compiler in ADA 83, but after the features of ADA 95 developed, they changed whole compiler into ADA 95 language. It will work on architectures which can support GCC in the backend and GNOT frontend supported at the same time. It can work on x86 and 64-bit architectures, and it will work on Linux machines also. This compiler contains two parts, frontend and backend. Backend is GCC to meet the needs of ADA, where there is need of exception support and all. Let's look at the front-end part. Front-end part contains 5 phases. They are lexical analysis, syntax analysis, semantic analysis, expansion, and GA phases. As in the traditional compilation process, lexical analysis, syntax analysis, and semantic analysis are same here. Lexical analysis, it is also called as scanning phase. Scanner scans the input string and generate associated tokens, which usually occurs in every traditional programming compilation. And syntax analysis, parser creates abstract syntax tree by verifying syntax of the token. Semantic analysis, semantic analyzer performs all static legality checks on the program, and it will check whether the value associated with the variable is correct or not, and decorates AST with semantic attributes. Expanding phase, this is the phase which is not usually we can see in traditional compilation process. Here expander is there. Expander transforms high level AST nodes which are generated after semantic analysis part. High level AST nodes are nothing but nodes representing tasks and protected objects and all into equivalent AST fragments. It will fragment into small ASTs with lower abstraction nodes. Expander calls to ADA runtime libraries if needed, and adding to that, every expansion activity must be followed by additional semantic analysis processing on the generated tree. We can see a backward arrow from expander to semantic analyzer in the figure shown. After expanding phase, GI phase transforms ASTs into a tree which can be read by GCC backend. This is the really an interface between GNAT frontend and GCC backend. In order to bridge the gap between ADA and C, several GCC code generation routines are extended and added to help that it will decrease burden on the GNAT frontend. All these phases which we are seeing are directly communicated only by AST. Surprisingly, GNAT does not use any symbol table, and all the semantic information of every program entity is directly stored in AST only. And also, the library runtime packages are not intermediately compiled units comparing to all other programming languages compilations. So whenever expander calls to library runtime routines, the compiler requires the specification of the package, and also it will start compilation anew. We can see source file is inputted into scanner, and scanner will break the strings into tokens, and parser will construct a syntax tree, and semantic analyzer decorates the tree, and it also checks in parser also. We can see a backward arrow which is going from semantic analyzer to parser, and this decorated tree is used by expander to make it into lower abstraction tree. And also it will use a semantic analyzer also, because uh, we don't have any symbol table. Expander has to use semantic analyzer also. And expander, there is a backward arrow from expander to parser. The reason is that when expander is calling library routines, we will get specification of the package which have to be compiled from the starting, which is not intermediately compiled units. So there is a backward arrow from expander to parser also. And we can observe that all the phases of scanner, parser, and semantic analyzer and expander are written in ada programming languages, and gi phase is written in C programming languages, and gcc is written in C. First we have syntax tree, and then we'll get decorated tree from semantic analyzer, and then this expander will expand the tree into lower abstraction syntax, and this will give us expanded and decorated tree. And GI phase transforms this tree fragments into a tree such that it can be read by GCC backend. Like in the compilation of traditional programming languages, source file is inputted to compiler, and it will generate one object code, and there are group of object codes which will be inputted to binder, and one object code is directly dependent on source file and will not be dependent on any other thing, and there is no dependency between one object code and another object code in terms of execution. So we can perform this execution of object codes in any order we like. So here there is a making of parallel compilation processes. Now let's see how this binder is useful. ADA establishes rules for valid order of elaborations. It is possible to construct a program where the order of evolutions is not possible. Such a program is treated as illegal and has to be diagnosed prior to execution of the program. That's where the binder came into existence, which performs the valid sequence calls to procedures and the bodies of the specifications of the ADA runtime libraries. Binder checks the consistency of program by looking at the timestamps of ADA library runtime information files. It operates in three modes, namely from ALI files only, from ALI files and any corresponding sources that can be located from ALI files, and all corresponding sources which must be available. We can see that from ALI files only mode is better than the modes 2 and 3. Despite the clear advantages of operating in source file mode, which is second and third alternative, it is more useful for the GNAT binder to operate in ALI files mode only. Not only this mode is faster, since no source file need to be accessed, but more importantly, it means the GNAT programs can be linked from objects even if the source files are not available. This feature is very useful when linking libraries that for proprietary reasons may be distributed without the access to the source file. Therefore, this mode is implemented in GNAT binder. And this mode is clear advantage comparing to 2 and 3. And this binder works as like a pre-linker. That is, prior to linker, this should be executed first. Now all these object codes will be inputted to binder, where it will check for consistency of the program, and then it will be loaded to linker, and linker will generate the executable code of the ADA program. Now let's look at the advantages and disadvantages of GNAT over traditional compiler. One of the advantages comparing to traditional compilation model is inlining is always done from source, as there is direct dependency between source and the object file, and so there is no requirement that inlined entity should be compiled first. And it is the binder responsibility, so it will check for consistency of the program. It is even possible for two bodies to define inline functions in each other without fear of circularities, that this function has to be executed for this function is to be executed, and like that, where there is no circularity is needed, and thus inlining works much more in flexible way than in traditional compilation model. Since GNAT is using same compilation as other language traditional languages, it is easier to build programs where parts of program are written in different languages, and these parts, if these parts are compatible with GCC backend, and surely we can write a parts of programs in different languages which will be used in GNAT compilation, which can be successful with GNAT compilation process. Moreover, GCC is not biased to a particular language, so it is easy to integrate ADA with any language that supports GCC. Order of compilation is dependent on source files, not on other compilation units, where it is dependent on other compilation units in traditional programming compilation model. The body of package cannot be compiled unless sources of its specification is available. This introduces parallel compilations compared to traditional compilations. And also another advantage is that GNAT is a open source software compiler. So the changes and the updations are done frequently, and this will leads to emerging growth of compilation models and compiler also. One of the main disadvantages of all these beyond all these advantages is that recompilation of library packages, which is not done in traditional compilations. We can see there is a arrow from expander, and there is arrow from expander to parser. That is where this library package recompilation works. When expander calls to library packages, this will move from the it is not like making the placing the compiled unit into the expander. It is like we first have to construct abstract tree of compile package also by taking from the source file, which is not done in traditional compilations. And this is how it is different from traditional compilation model. And this is the overview of GNAT compiler. Thank you for watching this.